which is on autoencoders. So, yeah. So let's start off with what is an autoencoder. So first of all, autoencoder is like a type of a neural network, which is like by which we can like compress data and use it to learn the more efficient parts of data and like extract the important features of the data. So it's like typically used for dimensionality reduction or like feature learning. And an important thing about it is that it is unsupervised learning, that which means that it doesn't need the truth tables for training. And like mostly the autoencoder, the basic two parts of it is the encoder and the decoder. So the encoder is like the part which captures the important features of the data and reduces the dimensions. And the decoder is like it rebuilds the data from the compressed representation or the data which is like extracted from the original one. So let's move on to what's the architecture of an autoencoder. So this is what typically an autoencoder looks like. So you have an input layer which like a certain nodes, you have a hidden layer and you have an output layer. So the input layer is like say suppose six nodes, you compress it to form only like three nodes or like say lesser number of like nodes. But due to this, it like extracts the features from it, like compresses the useful information and removes away the noise or the other randomness in the data. And after you have like the important data like encoded or like extracted, you use it to like generate the output layer, which is like generate the output closest like as similar as it is possible to the input layer. So this is what an architecture of a typical autoencoder look like. So first of all, we need to understand some terms within the architecture of an autoencoder. So first of all, we have an encoder. So the encoder is like basically you have an input layer with a certain number of data, which is like the data is fed through the input layer. What the encoder does, it's like so basically you have some hidden layers as well in this. So this is a traditional autoencoder. You might have like a certain hidden layers here as well. Like suppose you can have six nodes, and then the next layer you can have four nodes, and then three here, then four here, and then again six here. So the hidden layer can be here itself, like one or two here as well, like depends on how many input layers, like nodes you have in the input layer. So whatever like the hidden layer does is like it applies some sort of like transformations on the input data to such that it captures the most important patterns in the data. So it captures the data and then it like outputs it in form of a compressed vector, which is like in the latent space, which is like the center bottleneck of an autoencoder. So what is there like in the latent space is like you have a latent representation, which is like the representation of the actual data in such a way that the important features are stored in it and you filter out all the noise and the redundancies in the data. So this is mostly the part of an encoder, which is like basically like compressing the data and extracting the important features out of it. The second thing you have is the bottleneck. So it's like it is the smallest layer of the network in the data, which represents the most compressed version of it. One more thing that we need to understand is like the latent space or the bottleneck is not similar to the hidden layer. So what it actually means is like suppose like here we can have multiple hidden layers, but the one like the at the center of it, there's like a bottleneck created, which are where you store the most important features of the data. That is the latent space. And whereas you can have other hidden layers here or here as well, which like transform the data step by step such that it reduces its dimension. So that's mostly about the bottleneck. One more thing about is like yeah, it prioritizes the most significant features. And like the compact representation of the data helps the modern to like learn the structure in the best form because you extract the most important features. And based on whatever we have stored in the bottleneck, the data is like rebuilt or reconstructed in the decoder part of the autoencoder. So let's move on to the decoder part. So you have hidden layers which are like similar to the hidden layers in the encoder layer, but instead of like transforming data and reducing it, it's quite the opposite. You just like apply the transformations and on the data such that you extend the dimension into the higher dimensional space, which is like almost the like same. You just expand it from like say dimension 2 to like 784 again. So that's what the decoder layer does. And like the what's the most important part is like the decoder, like what the output of the decoder is in such a way that it's almost similar to the input. Like what the basis of the autoencoder is like to construct the output, which is like really similar and resembles the input. So the quality of the reconstruction also depends on how many layers you have and how well the encoder and decoder pair do. And you have to minimize the like the loss between the input and the output. So based on how well it is reconstructed. So yeah, does anyone have doubts still here? So yeah, I'll take it as a no. So first of all, these are like some important points about like autoencoders. So first of all, there should be like a high degree of correlation between the features of the data. So just like as we have like learned PCA, there should be some sort of correlation between the data because when you reduce the dimensions, it is like a necessary thing. If like all of the things are not correlated at all, then it would sort of not mean to like reduce the dimension. So just as we have learned in PCA that you need some features to be dependent on each other in such a way that you can reduce the dimension or combine few of them. Here it is like the same case. So that's the first thing. And apart from that, the autoencoder has unsupervised learning. And like during the training procedure, you like minimize the reconstruction loss, which is like the important thing is to understand is like in some sort of MNIST data set, what you do is like in a general neural network, you get like you have the input layer with like 784 nodes and you predict what is the value, like say 1, 2, 3, 4, 5, 6, 7, 8, 9, and you the loss is like measured in such a way that if the predicted value is correct or not, like you like do it based on which value it is predicted and what the image actually is. But in case of an autoencoder, the loss which we compute using MSE or any other loss function is the loss between the reconstruction, like how well it is reconstructed or how well it is like similar to the actual image. So that is the difference between the loss functions or like the loss between both of the things. So as I said, we use it you like use MSC or BSC to measure how close it to the input data. And one more important thing is that we usually add a regularizer which forces the model to learn the features and not just memorize. Say suppose if you have an input layer and you use an encoder decoder like basically an autoencoder. So what we do is like we add in regularizer such a way that it learns because really like the model can also like predict the same things in such a way that the weights and biases are adjusted such that you almost get the same thing. So we don't want the model to memorize like the thing. We want it to like extract the important things and like based on whatever we have extracted, it needs to like reconstruct it. So that is why we usually like add a regularizer to the logs function to ensure this. Yeah. So yeah, right now, so let's move on to the other part of the presentation, which is like PCA versus autoencoders. So which one is better in this case? So first of all, I'll just do a quick recap about PCA. So PCA is like a linear dimensional reduction technique. So you just find new axes like PC1, PC2 in such a way that it captures the maximum variance in the data, and you like project the data some say like five dimensions into like 2D space. That's what PCA is used for. And the important things that we need to keep in mind about PCA is like, you don't need training and it only captures linear relationships between the features because you find a new axis which is like a linear axis. So PCA only captures the linear relationship between the features. So and also it's like good for small data sets and like it the important part is like it cannot handle the complex patterns or nonlinear data well enough. And like if you compare it to autoencoders, so autoencoder is like you need to have a training for this, and it learns to compress the input and like reconstruct it again. So it can learn nonlinear and like complex relationships in the data. So suppose if you use like within the hidden layers and like in the whole neural network structure, if you use a linear function or a non-linear function, based on what you use, like say ReLU or like sig point, depends on that you can capture the data according to you. So that's an important thing about autoencoders that it can capture nonlinear data. And then it needs training, and yeah, we use the loss function like mean squared error and etc. such that you like capture or like find like basically ensure that the data which is like reconstructed is almost similar to what it was, like grasping the more like important features. So it's usually used for like the struct like when the data set is like high dimensional or like structured, and for low data set you can like even use PCA. So, yeah, before moving on to this, does anyone have doubts still here?
Yeah, one doubt. Do we use activation in the after the bottleneck layer?
Yeah, we can use the activation layer. So it's basically like neural network only. Like you have different layers. So based on that, even if they're hidden layers or something, you can use an activation function after any layer based on what you want.
Okay.
Yeah, so let's move on to like this part of the presentation. So what I did here is like this is like a comparison between PCA and autoencoders. So we used this following paper, which was like a very popular paper. So I'll just go through the data set which is used here. So first of all, we have the MNIST data set, which is like which contains the images of handwritten digits from 0 to 1, and each of the pixel is it's like a 28 cross 28 pixels, and like every image can be thought of as a 784 dimensional space or like a vector. So like we're using the data set because every image is like in 784 dimensions. So the goal of our like this thing is like to like ensure like we need to reduce this higher dimensional data in such a way like it's presentable or like representable in 2D. So this is what we are going to do. And like we'll use dimensional reduction in this for like two main reasons. Like we need to visualize it in 2D. We cannot visualize something like higher than 3D. So that's one thing. And then we need to compress data because we'll like remove the noise and we'll try to extract the most important features in it. So this is like the go through to the data set. And now I move to the comparison between PCA and like autoencoders on the real data set. So this is like PCA, and this is like using a two-layer autoencoder, like just from 784 to two dimensions without any hidden layers in between. And here we did not use any non-linear activation function. We just need a linear activation function, say ReLU or something. So we did not introduce the concept of non-linearity into this. So what we can see in this is like PCA ka graph, and this graph is like almost similar to each other. Like there's only a bit of difference. So what we can see in this graph is like the digits like 3 or 5 or like 6 or 7 are like very like close placed to each other. We cannot linearly like or any way we cannot separate both of them. It's like clustered, but like some other part like one or like say this darker part is like still away from the data set. So what we can see here is like using PCA we cannot like generally like distinguish or like find out which like we cannot get the clusters here properly because when we reduce the data like PCA reduces it in such a way that we cannot capture data in a very good way. Because of that we get these overlaps because in general if you have like a 3D space and you have a plane in it, it becomes a line in 2D. So because of that some points overlap each other. So that's the case in case of PCA because in some other dimension these point may be like away from each other, but as you go around like reducing the dimension in 2D, more or less you can see these very close to each other and you cannot find which one is which color or like which image. So this was PCA and this was two-layer autoencoder. So now we'll move on to like this basically we compare other different types of autoencoders and like how it works. So in the first case, they were almost more similar, and now we'll use this two-layer autoencoder, but instead of a linear activation function, we'll use a non-linear activation, and we'll use a deep autoencoder. So like a deep autoencoder is nothing but you use a different sorts of like hidden layers. So first of all, like that was like from 784 to 2 directly, you'll have different hidden layers in this, and slowly it will converge to 2. So this is a deep autoencoder, and we won't use a nonlinear activation function. This will have linearity into it, like say ReLU or something, and this will have a nonlinear function. So if we compare both of them, we can see that in this case it is much better. Like visibly we can't say, but yeah, you can see it's much better than the original one because this one is clustered much better, and you can see the difference. Like they're widely spaced. They were like more compact here in such a way that here it's like somewhat better, but you have a non-linear activation function. And in this case, what we can say is like a deep autoencoder, it's almost like all of them are like not widely spread, but they are like overlapped over one another. So this is one thing, like here you can see that these were like separate enough, but in this way you can see patches overlapped over one another. So this is the deep autoencoder. So we can see that this is like much better than this, or even more, both are like represent data in different ways. So if we introduce deep autoencoder and introduce a non-linearity into it, so in this case, it becomes a graph like this. You can easily see that there are like non-linear separation between all of them. And in this case, the it slowly converges to 2, and we use sigmoid in this. Because of that, these numbers, you can identify that, yeah, these images are of 1, these are like say 2, and these are like 8. So these digits are like like you can easily differentiate between them. And so when we use the nonlinear function, so it's represented in a great way, and we can see that the model using an autoencoder, it captures the data in such a way that all the features are extracted in a great way, and we can represent it using nonlinearity is also introduced, and you can represent it in a very well way. Whereas in PCA, you can't do anything directly. There is a lot of overlap. And because of that, we can say that autoencoder works really well compared to a PCA in a higher dimensionality task. So this is like the comparison of the performance between both of them. So like as I said, that PCA finds the directions and it's like linear, and you find the PC1, PC2 axis. Because of that, the digits like 0, 1 or 3 or 8 are overlapped, and because of that, there's like a lot of like it's much worse compared to this. And an autoencoder captures everything, and like you can have curves and loops here as well because of that, because of the nonlinearity, and it can represent the data in a much smarter way. So this is one thing, and apart from that, so yeah, this is like in the same research, in the same paper, this is the reconstruction using PC. Like this is the original LMNST data set. This is the auto like reconstruct the data through autoencoder, and it's this is what we like get when we reconstruct it using PCA. So in this case, like we had like the latent dimensional vector space being 30 dimensions, and like in autoencoder we reduced it from 784 to 30, and then reconstructed it from 30 to 784 again. In PCA, we did like from 784 to 30 and then 30 to 784. So what we can see is like using autoencoder it captures the data very well. Like you can see like to a human eye, it's like almost the same. But if you see PCA, you can say that, yeah, this 3, which was like in the original data, it looks like an 8 here. Or like this 8 is like, you can see this to be a 3. Or like this 6 is not good as a 6. You can see this line would like somehow represent this. Or like this 6 might look as the 5 here. So because of PCA, it's not able to capture it very well, whereas autoencoder like captures the feature in a much better way using nonlinearity.
Yeah, so I will be continuing with the training of autoencoder and discuss the variants of autoencoder which are used for variety of applications. So as we saw before that this is the architecture of autoencoder, and our aim is simple that we want to reconstruct the input X and want the reconstructed output to be as similar to as our input. So for that purpose, we will define a loss function between the input vector X and the reconstructed output X hat, and minimize this function during back propagation, which we do in neural networks as well. But there is a problem with this end-to-end training, which I will discuss here. So first is vanishing or exploding gradients. So as you can see, since there are a lot of layers, when you will do back propagation, then while updating the weights of this particular layer, there will be a gradient accumulation which will be tending to zero. So due to that fact, the weights in this particular layer won't be updated well. And since it won't be updated well, then the compressed representation of this input vector x won't be passed on to the subsequent layers properly. Second is slow or no convergence. Since you are not getting the optimal weights, the model will converge really slowly. So it is causing another problem. Third is overfitting, which will obviously happen since data is usually limited to us, and even if you don't correctly select the number of nodes in this hidden layers, then it could lead to identity mapping, due to which the model won't be able to learn the most important features or the most salient features which are present in the input representation. And the fourth point is the most important point for which this end-to-end training approach is not feasible, because earlier layers might not learn useful representations. And as you can observe that the weights keep adding on in the subsequent layers. So what is happening that the number of weights are increasing. So the number of gradient computations will also increase, which is a bit inefficient in case of computing. But mainly the fourth point is what we look out for. And to avoid these problems, we would be using the layer by layer pre-training approach. So what you do in layer by layer pre-training, you will first consider this input layer. That is, in the initial stage, you will consider this particular input. You will take an encoder and you will take the corresponding decoder. So what you aim to do is you aim to reconstruct the coded representation of the input X which is stored in this particular layer, and aim to reconstruct it using another decoder. So, for example, the input is X and the reconstruction is, let's say, X hat. So, by back propagation, you update the weights present in this particular layer and this particular layer. So, as you see, the number of layers are less here. So, the weights will converge faster, that is, they will reach the optimal solution faster. And the number of weights are also less, so it will be much more efficient computationally. And another reason is that you can see the rich features can be captured from this encoder of the input vector X, because the weights are learning, like the weights are converging quickly. So this is the steps which we follow in the layer by layer pre-training. We would be taking one layer of encoder at a time. At the initial stage, we would be taking this input layer, this encoder, and we would be taking the corresponding decoder. And through back propagation, we try to minimize the cost function between x and x hat. And in this process, it would be learning this. Uh, in this process, it would be learning these weights W1. After that, once this W1 is learned, you discard the decoder, because essentially we have to follow the architecture as it is. So we discard this decoder, and these weights are also stored for future reference, because we would also be going for end-to-end fine tuning later on. And in the next level of encoder, you will try to encode the Z1. So what is this Z1? Z1 is nothing but the output representation obtained from this particular encoder. So you are just repeating these steps for each and every encoder decoder pair. So this is the second step which we will follow here. We already have learned the weights W1. So now what we will do is we will consider the second encoder, and we will be considering the second encoder and take the corresponding decoder. And through back propagation, we would be minimizing the loss between this particular Z1, which is the output of encoder 1, and let's say X hat is produced as the reconstruction vector. So we will be minimizing the loss between this reconstructed vector and Z1. And in this process, the weights W2 will be learned. And similarly, you will store this W2 dash for future reference. So you repeat this process and you observe that you have learned all the weights present in the layer. That is, you have learned W1, W2, and W3. Now, once these weights are learned and once you have stored the weights obtained from the corresponding decoder pair, what you do is you do end-to-end fine tuning. Why this is required? Because you want to see how your model is performing as a whole, not only layer by layer. So you just go for the end-to-end fine tuning. Also, it is important that you adjust the weights globally, not just layer by layer, because you want to evaluate the model based on the whole architecture or the whole sequence of procedure which you follow. And another reason for faster convergence of this end-to-end fine-tuning is the weights which you have already obtained while the layer by layer pre-training phase. These weights are very close to the optimal weights for this whole architecture. So the convergence would be much faster compared to if you blindly go for the end-to-end training. And this layer by layer pre-training approach is also very computationally efficient, and it also allows your model to capture the compressed salient features of your input in a much better way, because the weights which you are updating don't just remain as it is because of the vanishing gradient problem. It instead gets updated according to what you desire. So this is the approach which we follow. That is, we follow the layer by layer pre-training, and then we move on to end-to-end fine-tuning. Then we would be moving towards the variants of autoencoder. So the first variant which we would be discussing is the sparse autoencoder. So what we observe that in basic autoencoder structure, we are reducing the number of neurons in the hidden layers subsequently and then increasing it. But it is not obvious always necessary that you need to reduce the number of neurons. You can also impose a sparsity penalty. That is, you can give the model freedom to decide which neurons it wants to activate and which neuron it doesn't want to activate. So, for example, if a particular neuron captures only a certain feature of the input vector X, then you keep it activated, and the rest neurons you would keep deactivated. Because what you want is you want to capture the most important features from the image. If you are taking all the neurons at once and you allow all the neurons to be active at a certain point of time, then there could be redundancy issues, or there could be issues pertaining to a bad latent space representation. So we impose a sparsity constraint here, which I will discuss further. This sparsity constraint's role is simple, that it aims to keep certain neurons active for a time. And this red one represents the active neurons, and this white ones represent the inactive neurons. So as I said, that salient features can also be learned even when the number of nodes in the hidden layer is large. So this is done by introducing a sparsity constraint. And what this sparsity penalty does is it causes the model to concentrate on the extraction of most relevant features from the input data. Because only a few neurons are active, and you have designated that a particular neuron will be reacting to a particular feature it faces from the input data. So you are essentially learning the most important and relevant features from a particular neuron, and you club all this information and represent it in latent space. So this is the objective function of a sparse autoencoder. So we are essentially adding a regularization term here, which is lambda times the penalty. The penalty is of two types, which I will be discussing. So since we are restricting the activation of the hidden layer nodes, this is done by adding a regularization term here. So there are two techniques for enforcing sparsity. We would be discussing the KL divergence penalty in detail. So L1 regularization is already covered in the previous session. It is just a penalty which is proportional to the absolute weight values, which are encouraging the model to utilize fewer number of features. What KL divergence does is you calculate the average activation of a what KL divergence does is it calculates the average activation of a particular neuron in the hidden layer, and estimates it from a hyperparameter, which is the sparsity parameter, which we would be defining for evaluation purposes. So as I said that in what you do in this case is that you consider a particular neuron, you calculate the average activation. That is, suppose this is the hidden layer H, and this is the ith neuron. So you compute the average activation of this ith neuron with respect to all the training samples which you have. So that is the Roje parameter which we define. That is, you take the average over all the training samples, and you take the uh, average activation for a particular neuron. So just to give you an intuition on what this hyperparameter, that is the sparsity parameter is, if you set this hyperparameter as 0.05, it essentially means that you want a particular neuron to be active only for 5% of the training time. So that is, for most of the inputs, the neuron should output a value close to zero, and only it should react to specific input patterns. Like it should not be reacting to all the features present in the input vector. It should react only to certain number of features. So what it helps in capturing complex or rare patterns, and also it improves the interpretability because you know which neuron is reacting to a particular feature or set of features. So what is your goal in this sparse autoencoder is that you aim to bring this average as close as possible to this sparsity parameter. That is the average of um, average activation of each neuron. You try to bring it as close as possible to sparsity parameter. So this is the objective function using KL divergence. So this is essentially the reconstruction loss, and this is the KL divergence term. This is the equation for KL divergence, and we will be looking at the graph of KL divergence versus this activation, average activation in further slides. So, and beta is nothing but it is the weight of sparsity penalty, which controls how strongly sparsity is enforced. So as I said that what I will try to give the intuition of what this Roje essentially means. So this Roje is zero point 0.8. It means that a particular neuron will be active only for 80% of the inputs. So if you compute the average activation for a particular neuron and you get the value of zero point 0.8, it means that it is active for 80% of the inputs. And let's say you have set the sparsity parameter as 0.05. That is, you want the neuron to be active only for 5% of the time. So when you just plug in these values into this particular equation, you will observe that the KL divergence becomes very large and it leads to a high penalty. And when you perform back propagation steps, you will aim to reduce the scale divergence term so that the loss function is minimized. So that's what I've written here. If a neuron is active for a long period of time, then its scale penalty becomes really large, and this forces the network to reduce the activation of that neuron in future epochs. And this is the graph of KL divergence versus the average activation of a node. So this is the on y-axis we have the KL divergence, on the x-axis we have the average activation of a particular neuron in the hidden layer. So let's say that I have set the sparsity parameter as zero point 0.2. So what this means is that I want a particular neuron to be active only for 20% of the time. So if we consider the previous example, let's say that average activation for a particular neuron is zero point 0.8. You can observe that the KL divergence is becoming close to 1. So what will the model do in the future epochs? It will try to reduce this KL divergence to like to make sure that both this rho and the rho j are, that is the sparsity parameter and this average activation, both of them are equal. If they become equal, then this scale divergence becomes zero. You can substitute the values and you can find out that it becomes zero. So that is the aim which we try to do. It is essential for interpretability of our model also. And here are the reasons why enforcing sparsity helps. First reason is the feature specialization, that is, each neuron is becoming selective and it fires only for specific input patterns. Secondly, it encourages neurons to learn diverse and meaningful features. And without sparsity, if there are many neurons which fire for a particular input, then it leads to overlapping or the useless features. Second point is that it prevents trivial representation. What happens is if there are no constraints, that you don't impose any penalty or any regularization term, then the autoencoder may just copy input to output. That is, it would lead to identity mapping, which we don't want because, uh, like, essentially these latent space representations which we obtain can be used for a variety of tasks. Like we can use them for classification problems or anomaly detection. So there are a lot of tasks which we want using this particular latent space or the information which we get from the bottleneck layer. So we just impose a sparsity constraint so that we improve the interpretability and also reduce the redundant features which our model is trying to capture. As I said, it improves interpretability as well because you know what each neuron has learned. Okay, so next I will move on to the denoising autoencoder. So what we do in denoising autoencoder is that we have a clean image. We add noise to the image. So essentially we are forming a corrupted version of our image, and we feed this corrupted version into the autoencoder. And the reconstruction, that is the reconstructed vector which we get here. So like the reconstruction vector which we are getting here, we measure the reconstruction loss against the original image because you don't want to reconstruct this noisy image. So what you do is you try to measure the reconstruction loss against the original image. This is a good way of doing it because, like the denoising autoencoder, the corrupted version of the input data is just like, for example, I said that we feed the corrupted version of the input data, and instead of comparing this corrupted version to the reconstructed output, we are comparing it to the original image and trying to minimize the loss between them, like as I said here. And the third feature is the most important for this because the model can't memorize the training data, as both the input and the output which you expect are different. So adding noise helps in reducing overfitting, which we have seen in many machine learning algorithms as well. So how it is done, that I will discuss in the further lecture. So the model learns a vector field to map the input noisy data towards the low dimensional manifold. So now the whole topic will revolve around what is this low dimensional manifold. So talking about a low dimensional manifold, consider that you have a space which is 28 by 28. Essentially, that you have 784 pixels in that particular space. So if I tell you to randomly pick a particular pixel and assign it either a white color or a black color, so the whole representation, if you look at the whole representation as a whole, you will observe that the image which will be formed will be very noisy and there won't be any uh, certain pattern which is followed. So that is what manifold hypothesis tells us. What a manifold hypothesis tells us is that even if you have a higher dimensional space, the meaningful images or the meaningful data is only present in the lower dimensional space. It is not present in uh, the higher dimensional space, because even if you consider the MNIST dataset, even in that the digits are not occupying the whole pixel representation. They are only occupying a fraction of space. So this manifold is essentially that fraction of space. And when you join all these pixels, you can represent this particular manifold as a curve in two-dimensional uh, space. So that's what I'm trying to convey here, that in the case of natural data, most of the valid data points do not span the entire high dimensional input space, but they rather lie on a structured low dimensional subset, which is called as the manifold. And this whole thing is explaining the manifold hypothesis. So this is the representation of manifold. As I said, that if you have a two-dimensional space, you can obtain the manifold as a curve, and on this curve lies your meaningful data or the clean input image, which lies in this particular manifold. And x tilde is nothing but it is the vector representation of the noisy data which we have. So, for example, this is the x tilde which we are passing into the auto, and X is nothing but the cleaner version of it, that is the clean image which we are measuring the reconstruction loss against. So this clean image or the meaningful image is lying on this particular manifold. And since you have added noise to the image, so this X tilde is getting separated from this particular manifold. It is no more lying on this manifold, it is getting separated from it because you have added noise to the image. So what is your aim during the minimization of cost function? Your aim is to bring back this particular vector X tilde to this manifold. So since we have added noise, you are not changing the semantic information present in the image. You are just disturbing the image through a certain parameter. It's not like the semantic meaning of the image is changing. So this X tilde will be close to this manifold. It won't be very far away from this particular manifold. If the two images are completely different, then the this X tilde will be lying somewhere here, which is far from this manifold. And you know that it is impossible to bring this particular X tilde back to this manifold because they are very far apart. So the agenda of this denoising autoencoder is that you feed the corrupted version of your input image and try to obtain the cleaner version of it. So this helps in variety of applications. If you have a certain image which has something spilled over it, then you can just pass it into this denoising autoencoder and try to get a cleaner version of it by reducing or by bringing this particular X tilde back to this manifold. So this is how the denoising autoencoder operates. And this slide is just summarizing what denoising autoencoders do. They take a corrupted input, that is input plus a noise, and reconstruct the original and clean input. And essentially, they try to create a vector field in this input space. As you can see, you are joining the X tilde and this X, and this is the vector representation. And this and it tells the noisy points how to move back to the manifold, which is done by minimizing the cost function. So this is just the 2D representation. We also know that these manifolds won't just simply be a curve because the vector would be, let's say, 100 dimensional or 200 dimensional. So this is just for visualization purposes. So yeah, if anyone has any doubt, please ask. So moving on to the contractive autoencoder. So contractive autoencoder is just like any other autoencoder, but it also has a penalty term which is added. So this penalty term is for mostly for the latent space representation. So what we want is if the input data is very similar, even if it has small disturbance, if you have small disturbance in the input data, then the encoded version of all those input data must also be very similar. That is, even if there are certain small changes to the latent even if there are certain small changes to the input, it doesn't cause any big changes in the latent space representation. This is what we aim to ensure in the contractive autoencoder by adding the penalty term. So this is the loss function in case of contractive autoencoders. This is the reconstruction loss which we have, and this is the penalty term added, which is nothing but the squared Frobenius norm of the Jacobian matrix. So I will be discussing what this Frobenius is and what this Jacobian term is exactly. And lambda is the hyperparameter which defines the strength of this penalty. So if you don't consider this penalty term and only consider this particular term, you will observe that there is no regularization on even like there is regularization only on what is the input and what is your reconstructed output. But essentially, what we are doing here is we are trying to impose a penalty on the activation of our bottleneck layer or the hidden layer. So by doing this, we are imposing a regularization on what the outputs of our hidden layer are. So this enables us to create better latent space representation because the goal of autoencoders is not just reconstructing the output image because we would be using these autoencoders for a variety of tasks like classification problems. So we want a better latent space representation, that is better clusters formed in the latent space. So even if we have certain changes in the image, it should be able to classify it. It should not happen like there is a small change in the image and it is classifying something else. So to ensure that this particular penalty term is added. So Frobenius norm in simple terms, if I try to explain, if you have a 3 cross 3 matrix, it would have 9 elements in it. So you have to take the square of all those 9 elements, add them up, and just take the under root. That's simply what a Frobenius norm is trying to convey. So what do you mean by the Frobenius norm of a Jacobian matrix? You take the square of all of these terms, add them up, and just take the square root of it. So this A1H is nothing but the activation of the first neuron in the hidden layer H, and you take derivative with respect to x1, which is an element in the vector x. Similarly, you will be taking this derivative with respect to all the elements present in the vector and for all the neurons present in the hidden layer. So this is the Jacobian matrix, and the penalty term which we are imposing on it is the squared Frobenius norm. So you will just be squaring these elements, adding them up, taking the square root, and then you will square it again to give the penalty term. One important observation which we should make in this contractive autoencoder loss function is that the two terms are contradicting each other. That if you observe this particular term and this particular term, they both have different meanings altogether because the reconstruction is telling the model to tell the difference between the input and the reconstructed output. This loss term is nothing but it is penalizing the model for uh, like it is incorporating the difference in variations which we have in the reconstructed output and the input. But what this Jacobian term is ensuring that even if there are certain variations in the input image, if they are very small, you aim to ignore those variations. So these two loss terms have particularly contradictory approach towards them. So this contradictory approach has to settle for a trade-off. That is, they have to settle for a point. So while this settling happens, we are able to capture the most important and essential information because this term is telling that you account for the variations present in the input, and this term is telling that you don't account for variations. So, what you are essentially trying to do, you are ignoring the redundant features and you are only capturing the most important ones instead of looking for any distortions or noise present in the image. So when you put these two contradictory conditions together into loss function, it enables us to train a network where the hidden layers now capture only the most essential information. So even in the latent space representation, you will observe that the clusters formed by the contractive autoencoders are much better compared to any other autoencoder architecture which we discussed so far because it is first of all it is considering the latent space representation because the purpose is not to get the best reconstructed image, rather it is to improve the latent space representation of our model. So it helps in following this. So it ensures that there are smooth clusters in the latent space and it is invariant to small noise and distortions. And there is a better separation between the classes. And the contractive autoencoders are trained to ignore irrelevant variations in the input and they capture only the essential features. So it makes them ideal for tasks like classification, anomaly detection, or semi supervised learning. Yeah, so this is the code implementation of the various autoencoder variants. So I will just give a brief overview of what I have done in this code. So I have taken a base autoencoder class. So I have defined the same architecture throughout for autoencoder which we will be using. And the other autoencoders which I would be defining is just inherited from this base autoencoder class. So because we want to draw comparisons on how the autoencoders perform and what specialty they have, to differentiate them, I have taken the same autoencoder architecture and just added the sparsity penalty or the noise to the image and the Jacobian penalty respectively in those blocks of code. So we are able to draw comparisons and take some meaningful information from these autoencoders. The dataset which I would be using is the MNIST dataset, which contains images of size 28 cross 28. That is, it contains 784 pixels, and I would be plotting certain graphs and comparing various metrics, which you will be able to understand through this implementation. So, yeah, apart from that, there are certain conclusions also we will draw through this code. So, the first block is essentially importing the necessary libraries which are required for overall implementation. And I have defined the base autoencoder class which we would be using or which we would be using for inheriting other classes. So I have defined the input dimension as 784. The hidden dimension is consisting of 128 neurons, and the latent space representation will be consisting of 32 neurons. So the bottleneck layer is 32 dimensional. So since I have decided to keep the same architecture throughout, so I would be considering the same architecture throughout, and then we would reduce these 32 dimensions into two-dimensional latent space by using techniques such as principal component analysis and TSNE methods. So we get the visualization of the clusters formed by each of these autoencoders. So this is the encoder implementation. This is the decoder, and in this we are just passing our input to encoder and decoder. And these are the variants of autoencoder. This is the basic autoencoder, which just computes the reconstruction loss. This is the sparse autoencoder where I have added the KL divergence penalty term here. And the loss term consists of the mean squared error loss and the KL divergence term. And the sparsity weight, that is the hyperparameter, is 10 to the power minus 3. And the sparsity parameter is 0.05. This 0.05 means that for how much training time, we want a particular neuron to be active. That is, we want only 5%. That is, we want a particular neuron to be active only for 5% of the time. This is the denoising autoencoder. We just added noise to the input image. Then this is the contractive autoencoder. In this block of code, I have just computed the Jacobians of the hidden layer activations with respect to the input. And this block of code is just loading the MNIST dataset. There is a train dataset and the test dataset. And this is the training function. So just for handling the different autoencoder types, I have defined for denoising autoencoder as you are adding noise to your input. And for other, you are not adding the noise, you are just keeping the original image. So this is just to handle different autoencoder types. In the evaluation function, you are just defining the evaluation parameters. That is, you are drawing inferences. That is, you are using the test dataset and you are sending the test samples and computing the evaluations. And these are the visualization functions which I have defined, which we will be using throughout. So first is plot reconstructions. That is, we want to see the reconstructed output of each autoencoder. So I've defined this particular function. Then we plot the latent space because we want to visualize how the latent space is represented. And as I said, that contractive autoencoder is trying to uh, give better latent space representation that we will observe later as well. This block of code is just defining the legend, that is what each color in the latent space corresponds to which number or which digit. Then I have implemented a PCA here and TSNE method here. We know that PCA is just captures the linear relationships, so it won't be that useful to draw visualizations. So I use TSNE, which is much better for non-linear non-linearity. Then I have also plotted the training curves, which essentially tells you the how the loss is decreasing with respect to each training curve. And these are certain metrics which we would be using. That is, we would be plotting the bar graphs for the mean squared error, for the latent sparsity, which I will discuss what this latent sparsity is, and the latent standard deviation. So these three metrics we would be using for analysis purposes. And this is just the execution that we are training our model on. So I just like I just define the parameters which we would be using and implement the training. And I trained here for 15 number of epochs, and the learning rate I have kept as 10 to the power minus 3. So here the data set is being loaded, and you can observe that training is completed here. Then we plot the training loss comparison curves. So as we observe that in case of denoising, the loss is maximum for same number of epochs. This is a valid result because in denoising autoencoder, you are not giving the original image, rather you are giving a corrupted version of it. And then you are comparing the reconstructed output to the original image. So it is really difficult for the model to take a corrupted version of it and then reconstruct it in fewer number of epochs as compared to others, because others are taking the original image as the input and they're trying to draw comparison between that original image itself. So that is the reason why the denoising autoencoders are having higher training loss in same number of epochs. So this is one of the things which we can draw here. Second is the reconstructed image. You can observe that the original one has this particular reconstructed image, sparse one has this one. In denoising, we added noise to the image. So this is the input which is going on into the autoencoder, and this is the reconstructed version of it. This is the contractive autoencoder's reconstructed output, and this is just the latent space representation. So since we have 32 number of neurons in the bottleneck, we are using PCA to reduce these 32 dimensions into two-dimensional space, so we can visualize the clusters formed by each of the autoencoders. So as you can observe that PCA doesn't give any meaningful representation to us, but these are giving us certain meaningful representation. For example, if you consider the sparse autoencoder, as I said, that sparse autoencoder improves interpretability. So a particular neuron will be only firing for a particular feature that it obtains. So you can see that certain clusters or these certain representations are very far apart from others. For example, this particular uh, for these particular points are very far from this, and similar for the pink ones and the blue ones. So it is improving your interpretability. Denoising autoencoder's aim is to give you a better reconstructed output by getting noise from the input data. So it is not essentially giving you a really good latent space representation, but the contractive autoencoder is separating to much better extent, as it aims to add a penalty that if there are more variations in the uh, like if there are certain variations in the input data, then the clusters which are formed, if they are similar, they shouldn't be far away. So you can observe that in other features, you will observe that many of the points are dispersed here and there. But in contractive autoencoder, most of the points are together rather than being very far apart. So that is the conclusions which we can draw from these visualizations. Then we have computed the performance metrics. This is the mean squared error comparison. As we discussed that denoising would have higher mean squared error compared to others because the input is different and the output which we are expecting is different. Talking about latent sparsity tells you that how much percentage of time a particular neuron is active. So in case of sparse, you can observe that a particular neuron is active only for 14% of time. And this is obviously what we expect from adding the sparsity penalty. And denoising, you can see that there could be overlappings because essentially we have a noisy data, and then bringing that noisy data to a particular manifold is very tricky because there are a lot of uh, mathematical difficulties involved. So, but in sparse, we have set a penalty that we want a particular neuron to be active for a certain percentage of time. So that's why this particular graph is on lower side of it. Talking about the latent standard deviation comparison. So latent standard deviation is nothing but consider a hidden layer, and you have the output, you have the activated outputs from those hidden layers. So what you do is once you get the activated output for each and every neuron, you will compute the standard deviation for that. So if the standard deviation is more, then there is more variance in the features of the input data. So that's what we can observe here. In case of sparse, you will observe that for a particular neuron, there won't be much of variation because a particular neuron is reacting only to a fixed feature. It is not reacting to all the features. So latent standard deviation for sparse will be lower for a particular neuron. And in case of denoising and in case of basic autoencoders, since they are firing or reacting to all the features, so in that case, what is happening that they have higher latent standard deviation. So there is, and contractive essentially aims to get a trade-off of it. As we discussed earlier, that the loss terms in the contractive autoencoders are contradicting each other. So they settle for a trade-off. That is, they aim to capture more amount of features like basic and denoising, but also focus on ignoring the variations in the features if there are present. So contractive autoencoders give us a better trade-off of those features. And sparse, as I said, that a particular neuron is reacting only for like for set of features. That's why the latent standard deviation for it is particularly less. And this is just the summary that for each and every autoencoder architecture, we have the mean squared error, we have latent sparsity, and the latent standard deviation for all four of the architectures.